Hello viewers, welcome back to my channel, and today we are going to discuss a very important concept which is arithmetic pipeline. So we've already discussed about instruction pipeline. You have a separate video for that. You can please go back and view that. And today we'll see what is an arithmetic pipeline. So an arithmetic pipeline is basically used to speed up arithmetic operations execution. Okay, and if you remember, instruction pipeline is used to speed up the execution of instructions. So when you want to speed up the execution of arithmetic operations, then you use arithmetic pipeline. When you want to speed up the execution of instructions, then you move for an instruction pipeline. Okay, so as in case of instruction pipeline, we have different instructions and then we put them in parallel stages. Similarly, here we will have different arithmetic operations. Okay, and we will break the operations into different stages. It's very simple to understand. So we'll take a very simple example. We'll take an example of a ripple carry adder. So if you remember a ripple carry adder, what was it? So in that, basically you used to add different bits. I'll show you the diagram also over here. So this is a 4-bit ripple carry adder, as you can see, and in this, if you see what we have, for all the 4 bits we are adding them one by one, and this is more like a sequential adding, right? Because first of all you will add the 0th bit of, let's say you have two numbers A and B, then you are adding the 0th bit of A with the 0th bit of B, and whatever carry is being generated, you are forwarding it to the next stage. Okay, and over here in the next stage, or for the next bit, you will add it with the next bit addition, right? In this addition, what you are doing in this full adder part, you are adding the first bit of A number and first bit of B number, and you are adding the carry generated from the previous stage, right? Or from the previous bits addition, you will say. The sum of the bits, whatever the sum of bits you have, you will store it in as S0, or you will show it as S0. And then similarly the process repeats over here. The sum of A1 B1 is stored as S1, carry is forwarded to the next stage. You add the next two bits A2 B2, and whatever sum is there, you represent it as S2. Either you store it in some register or you display it, and the carry is generated to the next stage, which is C3. You add A3 B3 using full adder 3 FA3. The sum is S3, which either you can print or you can save, and the carry is represented as C4, the final carry over here. So as you can see, for a 4-bit number addition of or you can say for a 4-bit addition of two numbers, you required 4 full adders, right? So in this case, since the addition was sequential in nature, if you see, the worst case delay will be 4 into carry generation time, right? Because all these 3 full adders, they were inactive when this was taking place. So first the addition of, you can understand it like this, that first the addition of A0 B0 will take place, and then only the addition of A1 B1 will start. Then so one time delay over here, one time delay over here, one time delay over here, one time delay over here. So it's like 4 into T times, right? So 4 times carry generation time delay. So if you take the addition time over here as, let's say, capital T, right, or you term it as carry generation time in full adder, then the total delay is 4 into carry generation time, right? Now let's see how the pipeline will help over here. Okay, just before that, this is the generic case of how you add in case of a full adder, right? So as you can see in this case, the rippling of the carries gives a bad performance. What does it mean? It means that because the carries are being generated one by one or in a sequential manner, the delay is large. It is 4 times carry generation time, right? So in this case, one assumption also over here is that delay of a full adder is equals to delay of a latch or register. That will like take the assumption when we'll convert this ripple carry adder into a, when we'll convert this representation into a pipeline. So let's see how we convert it into a pipeline. Just a second. Okay, so this is the corresponding pipeline for this. So if you understand it very simply, what I've done is the same thing that you saw over here. I have just made it in a parallel manner, or you can say it was initially one after the other. Now also it is one after the another, but I have put it into different stages, right? I have converted into a stepwise manner, or you can say skewed manner, staggered manner, different synonyms, right? Just let's understand it, what is happening over here. Again, C naught, any initial carry is put in the full adder FA naught. A naught, B naught, we are adding it over here. Whatever is S naught, we are storing it in a register. Okay, so these black boxes, small black boxes, as you can see, these are all 1-bit registers. Okay, so initially whatever was the result, it is stored over here, and the carry generated C1 is forwarded to the next stage. In the next stage, the next full adder is active. So if you see, initially in the stage 1 there was only first full adder active, which was FA naught. Now in the next stage 2, FA1 is active, that is FA1 is adding A1 B1 bits. Whatever is the sum, it is storing in the register and forwarding the carry to the next stage. In the next stage, A2 B2 is being added, and the same process is being repeated. Now, important thing to note over here is, if you see clearly, like what is happening over here is that when this full adder was active, what was happening to the other bits? The other bits were simply being stored into registers. Similarly, when this full adder was active, there is no work to be done over here, because A naught B naught, we've already added it, right? But what is happening over here? A2 B2 A3 BT, they are just simply being forwarded to the next set of registers. So at every stage you need to note over here that only one full adder is active. Okay, now how can we take benefit of this pipeline now, right? Because at every stage only one full adder is active. So in order to maximize the efficiency of the pipeline, what we can do, we can do parallel processing here, right? So for example, when I have completed the addition of A naught B naught, I have forwarded the carry to FA1. I have stored the sum in this register, which will finally be sent into S naught, like finally we displayed as S naught. Then at this point, this full adder is free. Okay, so at when I'll like perform the addition of A1 B1 in the next stage, at that point of time I can also perform the addition of next set of numbers for their 0th bits. So listen carefully again. What I'm trying to say is that when I have completed the task of A naught B naught addition for, let's say, first set of numbers, okay, let's say I have two pairs of numbers to be added. Okay, for the first pair, when I have completed the addition of A naught B naught, I have stored its result, I have forwarded the carry, then I am done with the 0th bit addition of first set of numbers. Then I can move to the second bit of numbers parallelly. I can start adding second pair of numbers parallelly. Okay, so when I'll be adding the first pairs A1 B1 bit, at that point I can add A naught B naught bit of next pair of numbers. Okay, so I think that is very much clear. So in this manner, what will happen is that I am now parallelly performing the addition of many pairs of numbers. I am not only working with a single pair, now I am working with multiple pairs. So that is how we can take benefit of a pipeline. So in this case, if you try to analyze now, what will be the delay? Okay, so once the pipeline is full, again this is very similar to how we analyze the instruction pipeline. Okay, but coming back to this one. So once the pipeline is full, what do I mean by pipeline is full is that initially when at the very first time I'm adding A naught, B naught, these three full adders will anyways, they'll be inactive, right? Because for the first pair of numbers, I don't have the sum generated for A naught, B naught. I cannot work with these full adders, right? So once this is forwarded to this, this is forwarded to this, this is forwarded to this, at this point, okay, now parallelly when this is forwarded to this, you have next pair of numbers being added over here, okay. So parallelly, the previous full adders are now getting worked up, right? Now they are all getting busy. So that means once we have this entire pipeline full, at that point if you try to understand what will happen. So once we have this full for the first time, this C4 will be generated and we have the result ready for the first pair of numbers. Now try to think what will happen for the after the next clock cycle, okay. So once this is done, at this point, for the next set of numbers, this C3 would have been generated. So just after one clock cycle, or just after a delay of one carry forward, the delay that we considered over here, carry generation time. So just after one more carry generation time, you'll have another result ready, right? Because after that, what will be done? FA3 will complete the result for next pair of numbers. So again, after this is done, this will be ready for next pair of numbers, right? So what is happening over here then? That after a delay of one carry generation time, you are getting one result ready, right? So now what is the delay of this pipeline? It's just one carry generation time. Whereas what was it earlier? It was 4 times carry generation time. So we have improved the speed of this pipeline, right? We have improved the speed of this arithmetic operation. And by how much? Like if you calculate the difference, it will be 4 minus 1 upon 4, that is 3 by 4 times, right? 3 by 4 times you have improved its speed. Okay, how many times if you see? So it is 4 times slower. This one was 4 times slower, right? Okay. Coming back, what is the benefit? Benefit we've already discussed, that carry has been so we can parallelly start adding the 0th bit of the next set of numbers. We can get parallelly, we can sum many numbers together. Okay, so let's analyze. So let's try to analyze now numerically. So for example, the delay of a full adder, if we consider it as t time of a full adder, and delay of one bit register if we consider as t times L. So that is TFA means time it takes to compute the sum. TL means time it takes to store that sum in this register. Okay. Then the total of this sum, okay, this will be less than or equals to the clock period. Obviously the clock cannot tick to the next stage when this entire task is being performed. So because this complete task after one bit addition is performed and it is stored into a register, only after that we'll say the clock ticks, or the result is transferred to the next stage. Okay, so clock period T has to be more than equals to TFA plus TL. Okay, now after the pipeline is full, as we discussed, one result or one sum is generated every time T. Okay, so after each clock period, you will start getting the result of two numbers, or result of a pair of numbers, a pair of 4-bit numbers. So earlier the delay was 40. So that's what you have, that's how you have speed up the arithmetic operation. Now, where will it be beneficial? It will only be beneficial when you have vector addition or array addition. It will not be beneficial when you have simple arithmetic addition of only two numbers, when you just need to perform the arithmetic addition of two numbers, because then what is happening, there is no there is still some speed up, but there is not much benefit there. Okay, why? Because it will happen only once, right? And in that case also, if you see, the delay, like as I told you, for the first time these three full adders were inactive. Okay, anyhow they were inactive, no matter if they are in a pipeline, no matter they are being performed sequentially. So for the first time it's all happening as in a sequential manner only, right? So yeah, so when you have this kind of example, that is, you have you have 10,000 numbers to be added, 10,000 numbers to be added for, let's say, two arrays, right? So there are two arrays and there are 10,000 bits you can consider. So you can consider there are two numbers where you have 10,000, or there are two arrays, simply you have 10,000 elements to be added for them. So in this case a pipeline would help. Okay, because you have, or you can simply say, when you have lots of numbers and lots of bits. Okay, so in that case, obviously for such kind of numbers you will need arrays or vectors for representation. That is why I have written that a pipeline will help when you have vector addition or array addition, as we have large amount of bits to be added for each number or array here. Okay, so, and it will not be beneficial when you have individual arithmetic operations. So that's all for an arithmetic addition. Please let me know if you have any doubts in the comment section below. Also let me know if you would like me to make any such related videos, or there is some doubt in any of the segments. You can please drop comments in the comment section below. In case you like the video, please press the like icon, subscribe to my channel for more such videos coming up, and also press the bell icon. You can also now join the memberships for some member specific content. And thank you so much and happy learning.
More such knowledgeable content, don't forget to press like, comment and subscribe to my channel. Also press the bell icon to get notified at the earliest. And don't forget to join the membership to get access to some premium content only for members. Thank you.